Now we are going to discuss about Michelson interferometer, an instrument which can produce both types of interference fringes such as circular fringes of equal inclination at infinity and localized fringes of equal thickness. And this is the person Albert Abraham Michelson who invented the Michelson interferometer. And this is the experimental setup of Michelson interferometer. And this is the source, converging lens, beam splitter, compensating glass, and fixed mirror, movable mirror, and the two beams will reach this detector and produce interference pattern. And here we need a monochromatic source. And this is the ray diagram of Michelson interferometer. This is a light source, converging lens, beam splitter which is coated with backside reflecting coating on the backside of the beam splitter, compensating glass, fixed mirror, movable mirror, and which is graduated on a scale which is in millimeters and centimeters, and the two beams after reflection from M1 and M2 will pass through the beam splitter and reach the telescope. One beam after reflection from beam splitter will move to the M1 and reflect it back and pass through the compensating glass again and reach the telescope, and second beam after reflection from the back surface of the beam splitter will move towards M2 and reflect it back and again pass through the beam splitter and reach the telescope. Therefore, these two waves which are originated from the same incident beam, therefore they satisfy the condition for interference. That is, these are coherent waves which are produced by the division of amplitude. Therefore, here we will get interference fringes in the telescope because the fringes will appear at infinite distance. We are using the telescope. Here you can see M2 and M1 prime. M1 prime is the visual image of the mirror M1, and if the distance between visual image of mirror M1 and M2 is D, then we will get the visual sources at S1, S prime and SW prime at infinite distance, and therefore because the distance between the slits, the mirror sees M1 and M2, M2 and M1 prime is D, therefore at the distance between the visual slits is 2D cos theta, because the light traverses between these two twice, therefore it is 2D cos theta, and this is the angle of inclination. Therefore here we will get the fringes of equal inclination at different theta we will get different pattern, therefore we will get circular fringes, and this is the condition for minima and this is the condition for maxima, and we will get fringes of equal inclination called Heidegger fringes on the detector. And Michelson interferometer is used to measure the wavelength of light, and this is the condition for minima, and 2D is equal to m0 lambda when theta is equal to 0. Therefore, if you move the movable mirror from the position D to D prime, then the new condition is 2D prime is equal to m lambda when theta is equal to 0. Therefore, when the mirror is moved from D to D prime, therefore the number of the total distance, the path difference between the two positions is 2 into D prime minus D is equal to m minus m0 into lambda. Therefore, it is equal to n lambda. Here n is the number of fringes which are displayed at the center of the Michelson interferometer. Therefore, lambda can be obtained from this equation. Therefore, lambda, the wavelength of incident light, lambda is equal to 2 into delta D by delta M. Here delta D is the displacement of the movable mirror and delta M is the number of fringes moved across the field of view. And Michelson interferometer can also be used to measure the wavelength separation of a doublet which are having the wavelength lambda 1 and lambda 1 plus delta lambda. And if this is the condition for maxima, This is the condition for minima, for example, when theta is equal to 0. For the first wavelength, 2d1 is equal to p lambda 1, and for the second wavelength, q into lambda 1 plus delta lambda. If both if this is the condition for first wavelength and the second wavelength, therefore the fringe pattern is very bright when these two conditions are satisfied. Therefore, this is called concordance. If both the maxima overlap, both the maxima due to first wavelength and the maxima due to second wavelength, if they overlap, we will get maxima. Therefore, this is called concordance. And if you move the movable mirror slowly to a new position, and it will displace, and this is the condition for another maxima. Therefore, when you shift the d by half lambda, then you will get another concordance. If you move it by 1 by 4th lambda, you will get one discordance. Discordance means the maxima of the first wavelength will fall on the minima of the second wavelength, then you will get complete darkness. Therefore, fringe pattern will extinguish. Therefore, if you move further, again you will get another concordance. Therefore, the distance between two concordance or two discordance is called d2 minus d1. Then the condition, from these conditions we can obtain delta lambda is equal to lambda 1 square by 2 into d2 minus d1. Here lambda 1 is the wavelength of the first wavelength, first one wavelength in the doublet, or average wavelength of the doublet, and d2 minus d1 is the displacement to get two consecutive concordance or discordance. Therefore, by using Michelson interferometer, we can estimate the change in the difference in wavelength between two closely spaced spectral lines. And Michelson interferometer can also be used for measuring the coherence length of a spectral line. Here we will measure the temporal coherence length, and measurement of thickness of thin transparent flakes by keeping one transparent flake in one of the path. That will introduce an extra path difference. From that we can measure the thickness of thin transparent flakes. And if you keep transparent media in one of the path, the optical path length changes. From that we can measure the refractive index of the transparent media. And Michelson interferometer can also be used in laser interferometer gravitational wave observatories to detect gravitational waves, which is one of the important predictions of Einstein's general theory of relativity. Therefore, Michelson interferometer experiment is very important tool to observe gravitational waves. And Michelson and Morley proved that ether media does not exist by conducting experiment on Michelson interferometer. They proved that there is no shift, and therefore the result of Michelson-Morley experiment is the stationary ether is the hypothesis of stationary ether is incorrect.